You ever stop and think about the hidden chemistry that's literally all around us? Well, today, we're going to peel back the label on some of the most common sense and solvents you probably run into every single day, just to see what makes them tick on a molecular level. Let's get into it.
Okay, so this sounds like the start of a weird riddle, right? You've got a warm spice, a nutty flavor, and then this really sharp chemical. I mean, they seem like they're from completely different worlds, but today we're going to uncover this surprisingly simple chemical thread that ties them all together. And trust me, the answer is hiding in plain sight.
So here's our game plan for solving this little mystery. First, we'll look at the scents and solvents themselves. Then we'll dive into their core structure, learn how to name them, explore their properties and reactions, and finally, we'll bring it all home and see this chemistry in our everyday lives.
All right, so what is the answer to that big question? Well, the secret is in these two super related families of chemical compounds, aldehydes and ketones. These guys are the invisible architects behind so many of the things we smell and use every day. And here's the basic split. That amazing smell of cinnamon or almonds? Yep, that's thanks to an aldehyde. But that distinct kind of harsh smell of nail polish remover? That's acetone, a total classic ketone. So you've got two families with really different vibes. What on earth do they actually have in common?
Well, the answer is in their shared blueprint, their molecular architecture. Both of these families are built around one, single, really powerful feature that pretty much dictates everything about them.
And here it is. Meet the carbonyl group. It's just a carbon atom with a double bond to an oxygen atom. Simple, right? But you should think of this C double bond O as the molecule's command center. It is the absolute heart of both aldehydes and ketones, and it's the reason they act the way they do.
Okay, this right here, this is the most important difference. It all comes down to what's attached to that central carbonyl carbon. If it's got at least one hydrogen atom hanging off of it, bam, it's an aldehyde. But if that carbon is sandwiched between two other carbon atoms, then it's a ketone. A single atom. That's all that separates these two huge families of molecules.
So now that we know how to spot the difference, let's talk for a second about how chemists actually give these molecules a name. There's a really logical system to it, and once you see the pattern, it's actually pretty easy.
For aldehydes, it's super straightforward. You find the longest carbon chain that has the carbonyl group, and you just swap the E at the end of the name with al. So propane becomes propanol. And the best part? The carbonyl carbon is always considered carbon number 1, so there's no confusion. It really simplifies things.
Now, ketones follow a really similar pattern, but this time the ending changes to 1. So a 5-carbon chain like pentane becomes pentanone. The only catch here is that you need to add a number to the name to show exactly where that carbonyl group is, because unlike an aldehyde, it can be in a few different spots.
Of course, like a lot of things, some of the most famous compounds have nicknames. The simplest aldehyde is officially called methanol, but I bet you've heard of it as formaldehyde. And the simplest ketone, propanone, is what pretty much everyone on the planet calls acetone. It's the exact same molecule, just, a formal name and a common name.
All right, we know what they are, we know how to name them. Now we get to the really cool part. How does that super simple structure we just talked about actually change the way these molecules behave in the real world? How does it affect their physical properties?
Just think about it for a second. When you use nail polish remover, you feel that cold sensation, right? That's the acetone evaporating off your skin like crazy fast. So why does it do that? Well, it all comes down to how sticky the molecules are to each other. It's a concept that chemists call intermolecular forces.
So let's check out how this stickiness impacts their boiling points, using molecules that are all about the same size. Butane, which has really weak forces, boils at -1 degree Celsius. It's a gas at room temp. Propanol, our aldehyde, has that polar carbonyl group which makes it stickier, so its boiling point jumps to 49 degrees. But it's still not as sticky as an alcohol like propanol, which can do this super strong thing called hydrogen bonding, so it doesn't boil until 97 degrees. The bottom line? Aldehydes and ketones are kind of moderately sticky.
And that same stickiness also affects how well they can dissolve in water. See, that polar carbonyl group can grab onto water molecules. So the smaller aldehydes and ketones with just a few carbons dissolve really easily. But as that nonpolar carbon chain gets longer and longer, the molecule gets less and less water-friendly, and its ability to dissolve just drops right off.
So, okay, they have similar structures, pretty similar properties, but there is one huge chemical difference that sets them apart. And there's this classic chemistry test that can tell an aldehyde from a ketone in a really dramatic way.
It's officially called the Aldehydes test, but honestly, I prefer calling it the silver mirror test. Just think of it like a piece of chemical detective work. If you have an unknown substance and you think it might be an aldehyde or a ketone, this test gives you the answer, no doubt about it.
So here's how it works. You use this special silver solution called Tollens reagent. Now, aldehydes are really easy to oxidize. They react with this stuff no problem. Ketones, on the other hand, are way more stubborn. They resist oxidation, so they just sit there and don't react at all. So only the aldehyde is going to cause a chemical change.
And this is where it gets its awesome name. When that aldehyde reacts, the silver ions in the solution get turned into solid, metallic silver. And this silver coats the inside of the glass test tube, creating this absolutely beautiful, perfect mirror. I mean, you can't miss it. If you see a mirror, you've got an aldehyde. No mirror, no aldehyde. It really is that simple.
Whew. Okay, so we've gone through structure, naming, properties, reactions, the whole deal. Let's bring it all together and connect it all the way back to that first question we asked at the very beginning.
It all comes down to this number, 1. The presence of just one single hydrogen atom on that central carbonyl carbon, that is the dividing line. That's the one simple rule that separates the entire world of aldehydes from the world of ketones.
And just like that, the mystery is solved. The smell of cinnamon, the way nail polish remover works, it all goes back to that tiny, tiny structural detail. Whether a single hydrogen atom is there or not, that one tiny difference changes a molecule's name, its properties, its reactions, and its entire role in our world. It's everything.
It's just a really powerful reminder, isn't it? The world that we see and smell and touch is all governed by this invisible world of molecular structures. We've just seen how a handful of atoms can make all the difference. Kind of leaves you wondering, what other invisible structures are out there shaping your world right now?